Okay, so let's look at some of the acid-base equilibrium problems in the packet. So we know that when we are, like in problem 1 we did in class today, we had this weak base dissociation. And as long as it's in pure water, hang on a minute. As long as it's in pure water, we're okay. We know how to do that. That's the only thing there. You do your Rice table. You find X. X is hydroxide, so you get the POH. And you subtract from 14 to get the pH. So we can do all of that. It's when we get down to E that it turns a little bit tricky. Because here we're doing a titration. So in an experiment, 20 milliliters of this concentration of base, ammonia, was placed in a flask and titrated to the equivalence point. That means you're going to consume all of the base with the acid. And it's titrated to the equivalence point and beyond using that concentration. Okay? And these questions, some of them are going to be to the equivalence point, some are going to be before the equivalence point, and this one's going to be after, but you don't really know that yet. But these are different points, that's why they say titrated to the equivalence point and beyond, because they're going to change the volume of the acid that you add. Okay? But we're not going to worry about that just yet. Let's first figure out how to strategize to solve these kind of problems when we add an acid to a base. Well, the first thing we have to do, and if you look in your book, it gives you really good strategies. You have to let the acid react with the base. It is not an equilibrium. It is simply a stoichiometry problem in solution. So how do we get moles in solution? Boom. Volume times molarity. As long as they're giving you a volume and molarity, you can get moles or millimoles. Okay. So they want us to determine the volume of the acid that was added to reach the equivalence point. Well, the first thing I need to do then is I need to let the acid react with the base. And if we do that, then we are going to here's our information. So step 1, we're going to say ammonia is going to react with the acid. This is not an equilibrium, and it's going to donate the proton and make the ammonium ion and the chloride ion. There we go. That is the chemical reaction. And it's balanced, and I see that my acid and my base react in a 1-to-1 mole ratio. Because of that, that's how I get moles. So I tell the grader N equals V times M. Of the base has got to equal, if I'm going to go to the equivalence point, of the acid. This is at the equivalence point. I've added just enough acid to completely consume all of the base that I had in at the start. And what did I have in at the start? I had 20 mils of that concentration base. So 20 milliliters times the concentration of the base, that's how many moles I had of the base. They gave me the concentration of the acid. So can I find the volume of the acid? Sure. So the volume of the base that we were given is 20. And because I'm in milliliters, my volume is going to chug out in milliliters. And that's going to be millimoles per milliliter. And then I'm going to divide that by the molarity of the acid, and they gave me that here. 0.0120 millimoles per milliliter. And you see my unit cancels, and I'm left with volume units So I know I've set my calculation. So the volume of HCl is going to equal V times M of the base divided by the molarity of my acid. And when I do that, the volume of the acid that I'm going to add is going to be 20 milliliters times 0.018 divided by 0.012, and that gives me 30 milliliters. And so that answers part I. And that's my answer. Okay. So that answered part EI. Determine the volume of the acid that was used to reach the equivalence point. First thing I've got to do is show the stoichiometry, my mole ratio. Then I can come and say moles equal moles. So if I have this many moles of base in there, I know I've got to add that same number of moles of acid if I want to neutralize it. And solving for volume gives me that. So this is part EI. So check. Now we want to do the second part. It's a little trickier. Now they want us to get the pH of the solution after we've added 15 mils of that concentration of acid. So I haven't changed my concentration of my acid. It's still 0.0120 molar. Well, am I at the equivalence point, or am I before, or am I past it? Well, 30 mils of acid is the equivalence point. So if I'm only adding 15 mils, I haven't reached the equivalence point yet. So what would I have? I haven't reached the equivalence point yet, so I'm going to have this left over, and I'm going to have this salt that I made. So I've got a different scenario in part 2 than I had in part 1, because I'm still going to have this left over. So this is where we have to look at our steps here now. We're going to let the acid and the base react. Then we're going to calculate new concentrations of the species that are left over after the things react, and then we're going to see what kind of equilibrium we need to bring in to determine the pH. Okay. So for part 2, we're only adding, so I'm going to put my claim here. Part 2, we took 15 milliliters of 0.0120 molar HCl and added it to the, 20 mils. They've changed your problem on you, so we're not going back to, we're going to act like we've just added this to that all over again. 0.0180 molar ammonia. And I already know from part I that I'm not at the equivalence point. So I'm going to have some of this left over. HCl is limiting. I already know that because I haven't neutralized all my base. I need 30 to neutralize all my base. I'm not adding 30. I'm adding less than 30. So I know I'm going to have some base left over. It's going to be in excess. So what we have to do is we get our total volume. That's why they say the volumes, assume volumes are additive. So the total volume after I mix them is 15, and I've got to show the greater this, which is 35 milliliters. Whatever's left over now has this volume. It doesn't have 15, it doesn't have 20, it's now, you've mixed the two solutions, so you now have a total volume of 35. That's a point students often forget, that you have to, when you mix an acid with a solution of acid and base, you've got to add their volumes to get new concentrations. So now let's do our, see what we have left over, that plus this. So this is going to be my rice, but it's not going to be equilibrium. This is a chemical reaction, so I'm coming to an end. And sometimes it's easier to do this, stoichiometry. So what are my millimoles? So I already know I have 0.36 because I already did that calculation somewhere else. These are going to be in millimoles. So millimoles. We're not in molarity in the stoichiometry table. We've got to work stoichiometry in moles. So we know this because we already did it earlier, but I'll do it again. What's 20 times 0.018? It's 0.36. So we have 0.36 millimoles. How much of the acid do I have? 15 times that should be 0.18, but we'll say 15 times 0.0120 is 0.18. So that's what we had at the start. We didn't have any of that. Then what's limiting? HCl is limiting because they're in a 1-to-1 mole ratio and there's less of this. So we're going to use up all of that. We don't have any left over. It's going to react to 1-to-1 mole ratio. This produces that same number. And this is a spectator, but if you want to add it, fine. But we don't care about that. Chloride is too weak to change the pH. We're left with half of it. And here we've made that amount of the conjugate acid, and we really don't care about this, but just know we're not going to do anything with that number. So now we have to classify what's in the beaker. Leftover species. That's what's left over. Ammonia and its conjugate base. As soon as you see a conjugate acid base pair left over, you know this is going to be the common ion effect. And when it's a conjugate acid base pair of a weak base or weak acid, those solutions are given a special term. They're called buffers. So this will make a buffer. A buffer is a weak base and its conjugate acid. If both of them are in solution, you've got a buffer. All right. So where are we in our list? We haven't calculated the new concentrations, but we did let them react, and we're classifying the equilibrium that will determine the OH. So this is where we classify. We had the weak base and its conjugate left over. I know it's going to be a common ion effect. You always write the equilibrium not from the salt, but from leftover weak weak base. So we have this equilibrium. Now we're in equilibrium. We've totally changed. We let them react. We had this left over. Classifying my beaker, I'm like, okay, which equilibrium is going to determine the pH? This one. This is just an ion in common with this equilibrium. Because when we write this equilibrium, this is my base. It accepts the proton. I get ammonium ion and hydroxide. So you see here, this was left over from the acid and base reaction, so that's from the salt. And so you do have some of this initially. You still don't have any of this initially, but you have some of this from the salt that you made when you let the acid neutralize the base. And so this becomes my new rice table. This is my classification step. This is an equilibrium. Notice it's an equilibrium. So initially, I need my new concentrations. I'm going into an equilibrium table, so what do I need? I need new concentrations. So what are my new concentrations? The concentration of ammonia after reaction is going to be what's left over divided by the total volume after mixing these. My total volume was 35. And so 0.18 divided by 35 is 0.0051. I'll give 36 these, 0.000514 molar. Well, am I going to get a different concentration for that? No, because it's the same number of millimoles over the same volume. So it's also the concentration of the ammonium. It's just because we're at the half equivalence point. So you've neutralized half the acid and you've made that same amount of salt. So this is a special case, the half equivalence point of a titration. You'll always have equal molar amounts of the leftover base in this case and its conjugate acid. So what do we have at the start? At the start we have 0.00514. Don't care about water. We usually put 0, but I can't put 0 here because we have this from the salt. So we have to put its new concentration, which is the same. Doesn't have to be the same, but they set us up here so that it would be the same. So 0.00514, and we don't have any of that initially. We didn't have any hydroxide after the reaction. We only had this and that. And chloride is a spectator. Notice it's not involved in my equilibrium. Minus x plus x plus x, and so we get 0.00514 minus x at 0.00514 plus x and x. And now we get our Kb. So what did we determine the Kb earlier in this problem? It was 1.80 times 10 to the minus 5. We determined that in an earlier part. So we get 1.80 times 10 to the minus 5 equals x times 0.00514 plus x over 0.00514 minus x. Now don't get into thinking you can cancel these x's. You cannot, because addition and subtraction always stops any kind of canceling out. All right? Can't do it. And you see that we are 10 to the negative 3, 10 to the negative 5, so technically I shouldn't be making my assumption, but I still am because I don't have a calculator that can do the quadratic for me. So here we go. We're going to say then x equals, and I go back to my table, what was x? Hydroxide. So I'm going to tell the grader x is my hydroxide, which is going to equal 1.80 times 10 to the minus 5 times 5.14 times 10 to the minus 3 over 5.14 times 10 to the minus 3. And when I do that, I get that the hydroxide ion concentration is 1. That's going to cancel. 1.80 times 10 to the minus 5. Now, if I had a calculator, you know, I would go on and solve this with the quadratic and probably get a little bit different answer. But just for the sake of showing you how to do it, I'm not worried about that yet. So that's that. How do we get the POH? So to be linear with my work, I've got to move down on the page. Start a new page, so I'm going to tell the grader this is number 1, part E, II. Always label, and you can put continued for the grader. That would be helpful to them when you start a new page. Always put your problem number, what part you're working on, and that you're continuing it. And so we have, bringing from the other page, that was 1.80 times 10 to the minus 5 molar. So the POH equals negative log of that number. And which equals 4.74, sorry, I think. 4.4 if we go to 3 sig figs. Let's check it. Negative log 1.8 e negative 5. 4.745 actually. 745 if I round that. That gives me 3 sig figs. Alright, but they didn't want POH, they wanted pH, so I have to remember to subtract from 14. So I show the greater. If I want 3 sig figs, I'm going to put 3 zeros there. Minus 4.745. And that's going to give me, notice I'm not clearing my calculator, I'm going to put minus 14, knowing I'm doing it backwards, so I don't worry about the negative. 9.256. So that's my pH. Box that for the greater. Does that make sense? Well, what did I have left in my beaker? Yeah, I had the weak base left over. I had a weak base, so I already know my pH should be greater than 7. And was our pH greater than 7? Yes, it was. It was greater than 7, so my answer makes sense. And that's how to do part E2. So what steps did I use? I let the acid and base react. I found what was left over. I got new concentrations by dividing the moles left over by the total volume. And then I looked at what equilibrium to write. Since I had weak base left, I had to use the weak base equilibrium. And then we made our Rice table. We made our assumption. I did not verify that because I don't want to solve the quadratic anyway. But technically, I would do that if I had the time. And then check answers, see if they make sense. So we ran through all those steps in part E2. Now, where are we going for part E3? I want the pH in the flask after I've added a total of 40 mils of the acid. Well, where is that in my titration? 30 mils got me to the equivalence point. So that's where we're going to see that sharp increase in pH. And then it's going to level off, right? So I'm after the equivalence point. So am I going to have any of my weak base? If I've added more acid than I had moles of this? No. If I add 30, I don't have any ammonia left. So if I add 40, I definitely don't have any ammonia left. So what do I have left? I have excess acid. And so your pH is always based on your strongest acid present. So we already know it should be less than 7 because we've got strong acid in excess. So we're going to add 40 milliliters of 0.0120 molar acid to the same thing, 20 milliliters of 0.0180 molar base. Now, from a previous part, you don't have to keep redoing the same work. I already know that there's 0.36 millimoles of that base. How many millimoles of the acid do I have? And I can tell the greater from part what? What part did we calculate that? Well, we sort of did it implicitly here. 20 times 0.08 gave us, oh, here it is, 0.36 right there. So from part E2, from part E1 and 2. So I already know that. I don't have to show the work again. Here, I need 40 times 0.0120, and that's going to equal 40.48 millimoles of HCl. There we go. So I already see that I'm going to consume all that. So we let it react. So we have ammonia plus HCl going to the ammonium ion and the chloride. And if you want to think about it, you have 0.36 of this, you have 0.48 of that. So this is limiting. This is my limiting reactant now. Use all of that. It's 1-to-1 mole ratio, so we're going to use that much of that. I didn't have any of that there to begin with, and so I make 0.36, and I make 0.36. But again, this is a spectator. So at the end, remember this is my Rice end table. This isn't equilibrium. This is stoichiometry. The acid and base are reacting. So I don't have any of my weak base left. Well, I already knew that. I wasn't going to have that left over. And I have 0.12 millimoles of the strong acid. So this is strong acid HCl. And yes, I do have some of this. But it's not going to affect the pH. This is a stronger acid than that. So the pH is based on the strongest that's in the beaker. And that's a spectator. Oh, forgot my charge. Okay. So we have to know that chloride came from a strong acid, so it is a spectator. Because it came from a strong acid. It came from HCl. It's strong, so that makes this too weak. It's a spectator. It's not going to enter in the chemistry. So between the two acids I'll have left, this is an acid. Which one is stronger? HCl is stronger acid than NH4+. And so we base the pH on the stronger pH based on the stronger acid, or base depending on what we have. Left. So if I'm going to do that, this is no longer an equilibrium. The concentration of HCl then is going to be N over V, which is going to be, 0.12 millimoles over what? What's my total volume? This is a total volume. What did I add? Go back up here. I added 40 mils to 20 mils. That's 60 milliliters. So need to show the grader that you're adding those 40 plus 20, and then the concentration is going to be 0.12 divided by, and I know that's 60, right? I just have to show the grader. So it's going to be 0.002 moles. Okay, 100% dissociates, 100%. So the concentration of H plus, because it's 100% dissociated, is going to be 0.02 molar. So the pH then is the negative log of 0.012, which is, so if you never clear your calculator, it really speeds you up, 2.699. 3 sig figs. And it should be acidic because I have a strong acid left over. So this is not going to determine the pH. The stronger the acids left is going to determine. If I have a strong base left, it determines. Whichever is strongest in my leftovers, that's what I base my pH count